Everyone, I'm Steven Diademo from TU Munich, and I'm going to present today my unitary fun project called QuNetSim, which is a quantum network simulation framework. So before we get into it, I'll explain to you what is a quantum network. A quantum network is a collection of nodes connected via a network so that they can transmit quantum states between themselves. So what I mean by this is you have two parties for this case, in this depiction down here, Alice and Bob. Alice is trying to send quantum information to Bob, but she's not connected directly to Bob, so therefore they need to make use of their quantum network connection. Alice can put her quantum information into the network will route the quantum information, and then it will arrive at Bob. And this is what I mean by a quantum network. Another thing of a quantum network that I think is a defining property of quantum networks is that they need to allow these two communicating parties to share entanglement. So this means that there needs to be a way for that Alice and Bob to share entanglement even when they're not directly connected. And there's lots of research involving this, how to distribute entanglement in a quantum network and things like this. So this is kind of the heart of what quantum networking is. So then we get into QuNetSim. So QuNetSim is a Python framework for developing simulations of quantum networks that have both classical and quantum connections. So what I mean by this is, you can see this picture. We have again two communicating parties, Alice and Bob, and they can communicate both classical and quantum information in this network. So we saw this picture before. We have the nodes in the network routing the information. So in this case, the nodes in this network can route both classical and quantum information. And what QuNetSim does is it simulates or allows that users can construct arbitrary networks and run simulations of these kind of scenarios. So they can define the nodes in the network, they can define what the nodes do in the network, and they can define what kind of messages, they don't define what kinds of messages, but they have the ability to send any kind of message they want, just classical or quantum. So what exactly does QuNetSim do then? It, as just kind of stated, it allows users to create simulation of quantum networks, so they can define their own network topologies, and they can define the kind of types of connections between these networks nodes. QuNetSim also provides a toolbox for quantum computing tasks that are really common. For example, sending an EPR pair from one node to another. Maybe this is in general, if you want to implement this by yourself, it's probably a multi-step procedure, but QuNetSim kind of adds this ability to run these things in one line of code, and it handles all the backend work for the user. Other kind of tasks like teleportation or super dense coding, we kind of integrate this into the framework so that users can spend more time using tools that exist to build new protocols rather than re-implementing the same old things over and over again. And what it does is it's also adding a layer of thread synchronization, and this mimics the behavior of a network. So in a network, you have two communicating parties. They're running this together at the same time. There's no means of, series operations in series. They both send a message, wait for a response. The message can arrive on one end, a message is sent back, and there's kind of this like sitting and waiting, transmit and wait. Did it arrive, yes or no, retransmit, if not. This whole process of simulating a network, we accomplish this in QuNetSim with lots of multi-threading and allowing threads to run in parallel. But we also apply this layer so that the users don't have to spend so much time worrying about how to synchronize threads. We ingrain this into QuNetSim to provide a more realistic network simulation. So QuNetSim uses three components for now, anyways. Maybe in future we add more, but in the current state of QuNetSim, there are three components. The first is the host. So by host, I mean these nodes in the network, which I was describing before. These nodes that want to send and receive messages. They can also process and store classical and quantum information. This means they can generate qubits, manipulate the qubits by applying gates to them, and then transmit them and put them into the network to be routed to their desired receiver. these nodes can act in two ways. They can be an end node, which is running the application and receiving and sending messages and storing information. Or they can act as a relaying node in QuNetSim. And this means they're kind of like the middleman, where they have to relay packets forward. And these are a special case because they can be programmed to attack. For example, they can eavesdrop on the messages, they can manipulate them while they're en route, and you can perform, as I said, you can perform attacks on the packets in the network using these relaying nodes. And each node in the network can be programmed to run any particular program. We just use Python functions and they run asynchronously, and these nodes can be programmed to run custom protocols. So this is my brief depiction. You have a classical quantum processor. These kind of are your input-output to the network, and then you store quantum and classical information to be manipulated by these processors and stuff like that. So the next layer is the transport layer. So you can kind of see we're using this internet stack. Transport layer is responsible for encoding and decoding classical and quantum information. So it turns it into packets. This makes it a little easier for us because we can add packet header information, and then we know exactly how to manipulate and decode quantum or classical messages, even though they're using the same methods to be routed and things like this, if by default at least. Transport layer is also making sure that protocols that need entanglement to run have entanglement. So this is kind of like makes it a little easier for the user. For example, if they want to teleport a qubit, but they forgot to establish an EPR pair ahead of time, transport layer will ensure that this EPR pair is generated so that there's no message that says, oh, you didn't establish the EPR pair, please try again. You have to deal with these kind of small bugs. It just really makes it easier for users to run the protocols without dealing with all the small parts of creating protocols. It's more to keep things at a high level. So this is again a depiction of what I think of a transport layer. You have your host, Alice, with these processors. She wants to send an EPR pair, and the transport layer turns this into a packet and puts this packet into the network. So the next part of QuNetSim then is the network layer. Network layer performs routing. It can be programmed to use custom routing algorithms. So by default, it's the shortest path routing algorithm. But you can change this so that it's routing using a custom routing algorithm. So actually the network is composed of two layers, kind of, quantum layer and classical layer. And what this means is that maybe they're not layers, they're kind of on top of each other. So the quantum network can be different than the classical network. So we can route quantum information through different nodes because you can establish a quantum network that's different than the classical network, and therefore you can write different routing algorithms for different use cases and things like this. And these can be tested in QuNetSim. The network can also be programmed to be noisy. So it can drop packets en route, and because these hosts are sitting idle and waiting and kind of programmed to, users can program kind of a retransmission phase of the protocols if they want, and they can simulate this by adding noise to the network. And then they have kind of a method of reliability in quantum networks that they can test. And the network can also be used to do multi-hop entanglement. So by default, we turn this off because it adds more complexity to the system, makes things a little slower if it's not necessary to simulate this part. But when we turn this on in the network, then actual multi-hop entanglement using entanglement swapping procedure is actually happening in the network layer. And for example, in this picture down here, if Alice wants to send an EPR pair to Bob, first she has to establish EPR pair with Bob. Bob has to establish EPR pair with Eve, and then they can use this kind of combination of EPR pairs to perform entanglement swapping protocols such that Alice, at the end of this protocol, shares an EPR pair with Eve. And then QuNetSim is kind of simulating that entanglement swap behavior. So how does QuNetSim work under the covers? So as I said, it's using Python threading. So each host is a thread in a queue, essentially. What happens is a message gets put onto the queue. In this case, it's packets always. packets get put onto this message queue or this packet queue, and the host is constantly checking if anything is inside this queue. If there's something in the queue, then the host starts to perform an action. And yeah, so that's kind of like the multi-thread behavior. Every time an action is happening, thread is forked, everything is running in threads so that things can happen in parallel. And you really get this network behavior because there's so much multi-processing going on, multi-threading, to be precise. And the network is also in a thread. So a network is actually a singleton object. Each host shares the network. The network has, again, this kind of packet queue, and it's listening for things to come into this queue. And when something comes into the queue, then the network is triggered to run some protocol. And then that's kind of like the whole system. So everything is kind of in this picture where I have here. Everything is sitting and waiting. Is there a packet? No. Is there a packet? No. Finally, a packet arrives, and now things start ticking in QuNetSim. And then before the packets arrive, everything is just sitting idle and waiting. So this really, in my opinion, it really simulates a network because, we're always sitting and waiting for messages to arrive. Let's say we're sending a text message or something. The phone is always sitting waiting for messages to arrive. Things like this. So it really is like message transmission, message retrieval with this kind of waiting behavior. And we try to simulate this using Python. So for the quantum aspects of QuNetSim, so these qubits that we're transmitting in the network, we're using pre-existing qubit simulators. Well, at least at the beginning we were. So the first couple of qubit simulators we used were Project Q. So Project Q is quite well known. It's an open source quantum computing framework that is kind of developed in ETH Zurich. Next is the CQC Simulacron. So Simulacron is actually also a quantum network simulator. And we were using this in our first kind of use cases of we wanted to write some quantum network simulations, and we really wanted more features and we wanted it lighter weight. And therefore, that's how kind of QuNetSim was developed. But we still make use of CQC, which is their quantum backend, and it's quite good. So we also integrate that into QuNetSim. And then after we had these two, we thought we would really like to have our own quantum qubit simulator that is more lightweight and kind of based on some multi-threaded systems. So we have our own qubit simulator, which is also open source. And this is the default qubit backend of QuNetSim. And it's kind of it's lightweight, also designed for multi-threading. So it's having like read-write locks and stuff to prevent kind of multiple access and collisions and stuff like this. And we've designed QuNetSim such that any qubit backend, can more or less be easily integrated into QuNetSim. So we have this interface that we allow any qubit backend you just have to implement this interface with the qubit backend, and then QuNetSim will use that particular backend. So it's easy to kind of swap out the backends, and sometimes it's more efficient to use a different qubit backend than others. For example, Project Q is really fast, especially the compiled one. So if you want to run your simulations that are more fast, then Project Q would be your go-to. But if you have a lot of hosts doing a lot of communication, a lot of threads that need to be running, then EQSN is a bit better for this because in its standard form, Project Q is not really designed to be accessed by multiple threads, at least from what we've experienced. So the pros and cons of using QuNetSim, in my opinion, it's very high level, so it's easy for beginners to get used to. A lot of the instructions are really kind of like written in a high level so that beginners can kind of logically, intuitively build their protocols. They don't need to spend like a month or two learning about quantum networks ahead of time. It's designed in such a way that any beginner can kind of pick it up, and hopefully we've accomplished it such that beginners can easily use this to write their own, like learn about quantum networks and test protocols on their own. You can test routing protocols, which I mentioned before. It's quite easy to debug in QuNetSim. Well, I guess depends how complicated the system is, but we have lots of logging messages that appear that can be turned on or off, and you see every step of the the protocol. So if you want to debug a protocol, you can see step by step by step what the network is doing, and you can kind of use this to debug your protocols if you have any issues with them. It's quite easy to install and get started. So we have the Python library. You can just do the pip install QuNetSim, which comes with a script for generating an example. And with this example, you can build more. You can kind of use it as a frame to start building more complicated examples that you want. But it's to run a very basic example, it would take, I don't know, 1 minute to just install with pip and then run the templating script to run the script, and you have an example ready to go. And also it's in active development, so we're really working on this right now. We're starting to get external collaboration in our open source project, and I'm really persistent in checking, making sure there's no bugs, and if there's a bug report, I'm quick to address it. I think since I really want this project to be successful, I'm really active in monitoring the project. The downside of using QuNetSim, though, are the channel models are at the moment simplistic. Right now we're working on this. Actually, we're starting to integrate a layer for the channels and like the connections and stuff like this, so that they could be more realistic. For example, like simulating a fiber optic cable, or maybe over the air simulation or something like this. So we're adding channel models now, but right now in the latest version they're not released. Since it's using single processing, multi-threaded on your own laptop, it's probably not great for large scale simulation. So if you have like 100 nodes in the network, 100 hosts sending many messages, things will slow down pretty quickly. And it's lastly using a packet-based quantum internet model, which maybe is not realistic in the future. Maybe it is, but it's not yet decided. It's not a standardized method. But there are some proposals that are not using packet-based quantum internet, and therefore, like, maybe it could be in 10 years when the real quantum internet comes. 20 years, who knows? It's not based on a packet-based internet, and maybe the research done with QuNetSim is not useful. So who should use QuNetSim then? As I said, it's high level, so I think it's really good for beginners to use. On top of that is instructors, because they can use it to teach QuNetSim. And in this semester that just passed in TU Munich, we had a lecture about quantum networks, and we used QuNetSim to teach quantum network protocols. And we got the students to implement protocols like quantum key distribution, super dense coding, quantum teleportation from scratch, and things like that. So, and from, our surveys, if they're honest, they really like to use the simulation because it gives them something to build on their own. They get to learn with doing a hands-on thing rather than kind of reading about it and doing a pen and paper approach, which is also good, but maybe having many ways of learning is helpful. So I also think researchers can use QuNetSim. A lot of research papers about quantum network protocols are written in a high level in a kind of optimal scenario. And I think researchers can design protocols at a high level using QuNetSim for research-based, for just kind of protocol papers. Maybe they can't benchmark their protocols, but they can develop the protocols and test them. So I just give a quick example of what QuNetSim code looks like. So in this particular example, we define our first protocol for a sender. Sender protocol is sending 5 EPR pairs to a receiver. So we see in this line 12, the host is sending an EPR pair to this receiver and making sure the receiver acknowledges that the EPR pair is there. So this is a blocking, this line blocks because it's waiting for an acknowledgement. And when the acknowledgement arrives, if it does arrive, then the EPR pair is stored at the host, and then the host can fetch the EPR pair from memory, and then we measure it. So we kind of just repeat this 5 times. It's quite just like a example protocol, maybe not particularly practical. And on the receiver side, we have protocol 2. Receiver here is waiting for the EPR pair, so get EPR pair and wait 5 seconds for it to arrive. So QuNetSim is in real time, and 5 seconds is usually more than enough time. It's definitely more than enough time. And so it'll wait 5 seconds for an EPR pair to arrive from the sender. Once it arrives, then it's also measured, just for the example. If 5 seconds expire and no EPR pair does arrive, then this will be none and the EPR pair doesn't arrive. So this is kind of like a simulation of the network part that I was telling you about. So to run all these protocols together, usually the common flow is you get your network instance, you define the nodes in the network. So in this case, we have nodes A, B, and C. We connect up the nodes in the network, or the hosts. So host A, for example, is connected to B. Host B is connected to A and C, so we see these lines here. And host C is connected to B. And then we add all the hosts to the network. So now this is established. The network knows the topology now after we add all the hosts. And then we want to make host A the sender of this protocol and host C the receiver of this protocol. And then we just kind of write this line here. These two things will run in threads, therefore they're running at the same time. And then host B is kind of in the middle, so there's routing going on and things like this. This is a quick example of what QuNetSim code would be like. So we have our documentation, which we wrote, and you can find it here, as well as some further examples, all the code open source. We have maybe 10 to 15 examples that are a bit more complicated than that one. And you can really start to get into some more in depth. You can see how kind of protocols written in a research paper translate to QuNetSim code. So just to wrap up, what I think is the future of QuNetSim is really want to establish a quantum network simulation community. So you see classical network simulations like NS3 or Mininet, who have hundreds of collaborators, or I don't know, 50 to 100 collaborators working on these simulators. And there's a lot of functionality of these simulations, really robust, and that can only really come with many collaborators, unless I start working on this full time with maybe a group of 5 people. I don't know, who knows. But yeah, it would be really nice to have a community based on quantum network simulation. I'd really like to have a more graphical interface. So my envisioning of that is you have a browser application and you can kind of do a drag and drop, design your network, click on the host, write the code in the host, and just makes it much more intuitive, I would say. And I think that would make it much easier for instruction to teach students how to use a quantum network. You can kind of give them a really visual kind of interface to learning quantum networks. And finally, really improving the realism and performance of QuNetSim would be great. Like being able to run large scale examples and have really realistic models of quantum networks would be really great too. So that's it from me. If you have any questions, can take them now if there's time, or you can email me or connect with me on LinkedIn. So thanks.